Hello, it's Keith here, and this is lesson 1 of the so-called SuckShoot series of my assembly programming tutorials. We're doing PDP11 programming today again on the UKNC as usual, and this is called the SuckShoot series because in this series, and I've done it on a few different systems, we make a little game called SuckShoot, which you can see on the screen here. It's a kind of a duck hunt type game. We have a bat flying towards us on the screen, and we have to shoot that bat a bit loudly there, but we have to shoot the bat and it goes away and comes to a new position. As we shoot the bats, we get some score, but the bat gets faster each time. If the bat gets to the front of the screen, you'll see that we lose a life in the top corner there, and the bat will reset to a new position at the smallest size again. So basically this is a simple little game, very simple game, and it's combining a lot of different effects that we've been building up over the previous platform and multi-platform tutorials. We're using Chibi Sound, my sound driver. We're using the binary coded decimal driver from the multi-platform series. We're using the graphics setup where we've got 2 of the bit planes mapped to the main memory, because remember on the UKNC we've got this PPU, which is the peripheral processor, which typically handles graphics, but we can remap it so that our memory is available on the main system. We've also got the keyboard reading driver, again running on the PPU, again in the platform series. So we're really building everything together into what you can see here, which is, as I say, a very, very simple little game, but enough for a practical example. And as always, you can go to my website and you can download this and you can build it yourself, and you're welcome to use any of the code in any way you can benefit from. Go ahead, even if it's commercial, if you somehow manage that. Good luck to you. So what we're going to do is we're going to go over some of the code today. Now we're going to go over this in 2 parts. The first part, we're going to just quickly discuss the basics of the way that the code is structured. We're going to discuss the sprite routines, and we're also going to have a look at the title screen routine. In the second part, we're going to go over the other code, but we're not going to go over that stuff that's been covered in the other episodes. So the binary coded decimal driver, the keyboard driver, etc. All of that's been covered before. So please see those episodes if you need to know how those parts work. It's just the SuckShoot code itself we're going to see. Okay, well, let's go over to our source code and let's take a look. Okay, so here is the start of our program here. So we've got the start at the very beginning here, and the first thing we're doing is we're initializing our drivers, and we've got 3 drivers we're installing on the sub-processor. The first one is the initialization of the graphics here. We're transferring this program to the sub-CPU. This will set up the graphics and it will then return. Once the graphics are set up, this program is no longer needed, so it can be removed from memory. The second one here is we're installing our keyboard interrupt handler here. This is set up as an interrupt, so it's running at all times on the sub CPU, which is the only one that can access the keyboard, and we're using that for our input. Now the third one is the Chibi Sound driver, which is executed and it continues running at all times. So the PPU is, while not doing those interrupts, is now entirely running the Chibi Sound driver for the sound effects. All of the graphics are done on the main CPU, so that's something important to note. Okay, so we'll just quickly go over the title screen and then we'll have a look at those graphics routines. So the start of the show title here, we've got a clear screen routine, and that's just clearing out the video memory. Let's just quickly have a look at it. So here it is. So once we've set up our screen with that command we executed at the start, our screen memory is on the main CPU at memory address 1 and 5 zeros here. That is now the VRAM base of our screen. Now there are 2 bits per pixel because we now have a 4-color screen, and so we need to clear this many bytes here for us to clear the entire visible screen. So we're just repeatedly wiping that memory there. That's how we're doing our simple clear screen there. Now our title screen, which you can see here, has the title SuckShoot, it has the flying bat, and it has the high score with the title high score. And we've got this locate and print string routine here. We're specifying an X and a Y coordinate in characters here. We're printing the title, then we're printing the score text, the message high score, and then we're locating again, and we're then using the BCD routine that we did in the multi-platform series to show the high score to the screen. And being as we've played now, we do have a high score, so we've got 10 points there. Well done to us. Now once we've done that, we're going to show the bat to the screen, and we're using the show enemy routine here, which we're going to see in a minute. However, we need to configure this so that it shows the bat in the correct form. We want the bat to be as big as possible, and we want it to show the 2 frames of animation. So we're setting our X and Y position. Now all coordinates within this game work on the center of the sprite, so we're not specifying the top left, we're specifying the center, and the reason for that is the range checking routine, so that we can do the collision detection of when the player's cursor is over the top of the bat. So we always work on the centers there. We're setting the scale, and we're setting the scale to 48 in decimal. This is effectively the Z position. The back goes closer to the player, so the Z position, we need it to be the biggest, and 48 is the highest. So this is basically selecting, by effect of having that biggest scale there, the largest sprite there. We're setting the enemy sprite to 0. That will always be the 0 or a 1. It's toggling between the 2 frames of animation, you see. Now here is our main loop here, and all we're doing here is we're XORing the enemy sprite here between 0 and 1. We're showing the enemy, we're waiting for a while, and we're showing the enemy again, and that's because we're using XOR sprite. So showing the enemy twice in the same position will remove it the second time. Now we don't actually move the sprite, but of course we are changing it, so we do need to remove it before our loop. We're then reading in from test ky+1, which is the memory in the main CPU's memory that is set by the interrupt handler on the sub-CPU. So this is automatically being updated all of the time whenever a key is pressed on the keyboard, and we're waiting for the space key, which is effectively our fire. Now, when this is not pressed, we are jumping back to the main title loop, and we are continuing to animate that back. But when it is pressed, that's when we spring into action and we start our main game loop. So that's how we're doing things. Okay, so that's the title screen, and we've had a very brief description of how the sprites are shown on the screen. But let's now go into detail about the sprites that we're using now. As always in my tutorials, I use Sprite Editor to export all of the sprites for my games. So here is the sprites that we're using, and we've basically got 7 in total. Sprite 0 is the player's cursor. 1 and 2 are the 2 biggest bat frames. 3 and 4 are the medium-sized bat frames, and 5 and 6 are the smallest. So these have all been exported with Sprite Editor, and I think it's, if we go to here, PDP11, UKNC, and we've used save raw 2-bit planes for our 4-color graphics here. Now the other thing we've exported though is, if we go to the right page here, we have this information here on the actual sizes of the sprites. And we've got this export info option here, which will actually export that as a table basically in an assembly format. Now I did have to make a few slight tweaks to it, but this sprite info table is pretty much a direct export of that. And so what we have here is offsets based on the size of the sprite in bytes, and these are calculated from the sprite base, and the sprite base is the data that was exported from that save option. So the sprite base is the raw bitmap data of all of our sprites. The sprite info table, the first 2 bytes, is the offset for that sprite within that table. And then the next 2 bytes are the width and height in pixels, not in bytes, in pixels. So we might need to convert that depending on what our program's doing, and in this case we definitely will. So when we want to show a sprite to the screen, firstly we're going to have to calculate the sprite to show with regards to the enemy bat because of the 3 different sizes and the frame animation. Then we're going to have to load in the source memory address of the sprite bitmap. We're then going to have to center the sprite, because remember we're specifying the center position, but we will need to subtract half of the width and height to start from the top left of the sprite, and then we draw in a zigzag left to right, top to bottom format, and that's how we get our sprite to the screen. So let's have a look at that sprite routine. Okay, so the complex one is show enemy, but for simplicity first, let's just have a look at show player. So show player is a very simple routine. All we need to do is we need to show sprite 0, and we show it at the XY position R1, R2. So here we are just backing up all of our registers on the stack so we don't change any. We're setting R0 to 0, we're showing sprite 0 here, and we run the show sprite routine. Now the show sprite routine will immediately multiply R0 by 4 to calculate the offset for that numbered sprite within the sprite info table. What it will do next is it will load in the width, and then it will effectively halve that. It converts it to a number of bytes and it divides that by 2. And this is so we can calculate the top left position for our sprite when we draw to the screen. Then we are loading in the height. We're halving that again, but this is of course in lines, so effectively the same as pixels. But then we are then subtracting that from the Y position, and this has converted the X and Y position to be the top left of the position we want to draw. Now what we're doing next is we are converting that to a VRAM memory address. So we've got our screen base here. We are effectively multiplying the Y position by 120 in octal, which is the number of bytes per line, 80 bytes per line for this screen mode. So that is calculating our Y position. Now there are 2 bit planes, so there's 2 neighboring bytes. which make up the 2-bit planes for the pixels, and so we are multiplying our X position by 2 to convert that so that it matches. We're adding those together, and this has effectively calculated the memory destination for our sprite. So now all we need to do is get the source for our sprite, and we're moving that out of R5 because R5 points to the start of the data for this sprite. The first 2 bytes are the memory address of the sprite data. The next byte is the width of the sprite, and the next byte is the height of the sprite, and so we are reading in the 2 bytes of the source memory address into R4 here. We are then loading in the height of the sprite into R3, and this is for our loop counter. We're then loading in the width of the sprite into R2 for our other loop counter, and we are then converting that to bytes here, and so we're then going to transfer and XOR the bytes from our source bitmap to our screen, repeating once we've done an entire line. Now once we have done an entire line, we're moving down a line by adding 80 in decimal to our current VRAM destination, and we're repeating until we've done all the lines. Okay, so that's how we're drawing our sprite. So the last thing we need to just discuss is how we're calculating the enemy sprite offset, because of course we need to convert our frame number and also our scale to be a sprite number from 1 to 6 to pass to that routine to calculate. So what we're doing here is we're loading in the enemy scale. Now the enemy scale, unfortunately, I guess when I created the table of sprites I did it the wrong way around. I should have started small to big, and instead I started big to small. So rather than redo the sprites, I've done it in code here. So we're basically flipping all of the bits of R0 here to compensate for that, and we're then shifting the bits into the correct position, and we're doing a bit clear because basically we want to have a multiple of 2 here, because of, remember, there's 2 frames of animation for each sprite. So we're only keeping these 2 bits here after the bit shift, and this is effectively selecting one of the scales based on the 2 most significant bits of a range of 0 to 48 in decimal. That's why we specified 48 before. And then what we're doing here is we are loading in the frame number, which will be either a 0 or a 1, and we're adding that to that base. We are skipping the first sprite because sprite 0 is the player's sprite, but this is now calculated the correct sprite number. As I say, it's going to be 0, 1, 2 or 3, and we'll multiply it by 4 to get the offset in the table later. We're then just loading in the X and Y position of the enemy here into R1 and R2. We are of course backing up R1 and R2 before we run this routine, because the general code expects R1 and R2 to be the player's position, so that's why we're doing that. Anyway, that's all of the code that's handling the sprites. The code's a bit of a pain to get working, but it's quite flexible, and of course if you wanted to use this code in your own programs, I'm not saying you should, but if you wanted to, you can of course do so, and you could create your own table with the export info option from Sprite editor. As I say, you can export the bitmap data from the UKNC option, and you know, I will certainly be using this as a template if I do any more games on the UKNC. Anyway, I hope you've enjoyed what you've seen today. If you have, please like and subscribe, because if you like the videos, YouTube recommends them to more people, and if you subscribe, I have a happy day and I think about making more videos, so everyone benefits from that. Anyway, hope you've enjoyed what you've seen today. As I say, go to my website, download the source code and build scripts, and have some fun with it. Thanks for watching, and goodbye.